For the lesson 3.5, polarization. Polarization is characteristics of all transverse waves. For a string that in equilibrium lies along the x-axis, the displacement may be along the y direction. So this is the x and the y-axis. The transverse waves is like this, right? And the string lies along the x-axis, the displacement will be this waves. In this case, the string always lies in the xy plane, but the displacement must instead be along the z-axis as in figure 3.18b. Then the string always lies in the xz plane. So there's a z plane in here. So this is the y, this is the x, and this is the z, just like in here. So 3.13a, transverse wave linearly polarized in the y direction. So linearly polarized in the y direction. Y direction is upper, so pag ganon. And so B, transverse wave linearly polarized in the z direction. So there's a transverse wave in the z direction. This is the z, so pag ganon. And so C, the slot functions as a polarizing filter, passing only components polarized in the y direction. So if there's a scattering of light in here and you have a slot na mayroong y direction, only the light that has a y direction will go through it. So making a polarized wave on a string from an unpolarized one using a polarized filter. So this slot is called polarizing filter. When a wave has only y displacement, we say that it is linearly polarized in the direction of y. A wave with only z displacements is linearly polarized in the z direction, as in these figures A and B. For mechanical waves, we can build a polarizing filter or polarizer that permits only waves with a certain polarization direction to pass. In figure 3.18c, the string can handle slide vertically in the slot without friction, but no horizontal motion is possible. And this filter passes waves that are polarized in the y direction but blocks those that are polarized in the z direction. Polarizing filters, waves emitted by a radio transmitter, are usually linearly polarized. The vertical antennas that are used for radio broadcasting emit waves that in horizontal plane. So the waves pala is in horizontal plane, pag ganon. Around the antenna, and they are polarized in the vertical direction or parallel to the antenna. So there's a polarization filter in here. So the situation is different for visible light. Light from incandescent light bulbs and fluorescent light fixtures is not polarized. So, iba yung situation when we are talking about visible light and doon sa invisible wave. Because waves can either be visible or invisible. When we say invisible, it can be a transmitter wave or or a signal, okay? And when we say visible, it can be a light, incandescent, from the incandescent light or fluorescent light. Figure 3.19a, electrons in the red and white broadcast antenna oscillate vertically, producing vertically polarized electromagnetic waves that propagate away from the antenna in the horizontal direction. So, ang ating electromagnetic waves are vertically polarized. They are vertically polarized that are traveling horizontally from the antenna. The antennas that radiate light radiate light waves are the molecules that make up the sources. The waves emitted by any one molecule may be linearly polarized, like those from a radio antenna. But any actual light source contains a tremendous number of molecules with random orientations, so the emitted light is a random mixture of waves, linearly polarized in all possible transverse directions. Such light is called unpolarized light or natural light. To create polarized light from unpolarized light, natural light requires a filter that is analogous to the slot for mechanical waves. Polarizing filters for electromagnetic waves have different details of construction depending on the wavelength. For microwaves with a wavelength of a few centimeters, a good polarizer is an array of closely spaced, parallel conducting wires that are insulated from each other. Think of a barbecue grill with the outer metal ring replaced by an insulating one. Electrons are free to move along the length of the conducting wires and will do so in response to a wave whose electric field is parallel to the wires. So I will explain this one later. Where am I? The resulting currents in the wires dissipate energy by I squared R, or the power energy is this is P, di ba? P is equals to I squared R, heating, from your electricity and magnetism. So, subject. The dissipated energy comes from the wave. So whatever wave passes through the grid is greatly reduced in amplitude. Waves in electric field oriented perpendicular to the wires passes through almost unaffected, since electrons cannot move through the air between the wires. Hence, a wave that passes through such a filter will be predominantly polarized in a direction perpendicular to the wires. The most common polarizing filter for visible light is a material known by the trade name Polaroid, widely used for sunglasses, and polarizing filters for camera lenses. Developed originally by the American scientist Edwin H. Land, this material incorporates substances that have dichroism, a selective absorption in which one of the polarized components is absorbed much more strongly than the other. As in figure 3.20, it is a Polaroid filter. So the filter almost completely absorbs horizontally polarized component of the light, and it only transmits light in the vertical direction. So the light that is horizontally oriented is absorbed, and yung kanyang nire-reflect out niya lang is ang vertical or vertically directed light. A Polaroid filter is illuminated by unpolarized natural light. So this is the unpolarized natural incident light. It will enter the Polaroid filter, and it only filter only partially absorbs vertically polarized components. So some of the vertically directed light is absorbed, but is also reflected out. Pero yung ating horizontally directed na incident unpolarized light is inaabsorb niya. Para siyang tinatrap. Okay. So, next. Using polarizing filters. An ideal polarizing filter or a polarizer passes 100% of the incident light that is polarized parallel to the filter's polarizing axis, but completely blocks all light that is polarized perpendicular to the axis. Basta polarizer siya. Alam ko na medyo naguguluhan kayo dito, pero the point is, it is a filter, again, it is a filter that traps incident unpolarized light, and only one direction lang yung kanyang pinapalabas. Like, in this case, vertical light. In figure 3.21, unpolarized light is incident on a flat polarizing filter. The electric field vector of the incident wave can be represented in terms of components parallel and perpendicular to the polarizer axis, shown in blue. Okay? Now, only the component of the electric field parallel to the polarizing axis is transmitted. Hence, the light emerging from the polarizer is linearly polarized parallel to the polarizing axis. Again, this is the polarizing axis, the blue one, and this is a polarizer. What is a polarizer again? It acts like a filter. So from this incident unpolarized light, only the light with the same angle or with the same polarizing axis will pass through it. So in this case, this light in here, transmitted light linearly polarized parallel to polarizing axis. When we say parallel, they are of the same angle. The intensity of the transmitted light is the same for all orientations of the polarizing filter. For an ideal polarizing filter, the transmitted intensity is half the incident intensity. So in this figure 3.21, unpolarized natural light is incident on the polarizing filter, and the photocell measures the intensity of the transmitted linearly polarized light. So the photocell will only measures this intensities. Okay. So I have explained this figure. Next, what happens when the linearly polarized light emerging from a polarizer passes through a second polarizer or analyzer? Again, there's another polarizer. Suppose the polarizing axis of the analyzer makes an angle phi with the polarizing axis of the first polarizer. We can resolve the linearly polarized light that is transmitted by the first polarizer into two components as shown in figure 3.22. So, in this case, an ideal analyzer transmits only the electric field component parallel to its transmission direction. So from this polarizer, there's an incident, so inabsorb niya lang na light is parallel into this blue line. So ito na siya. Pagdating sa next analyzer, si analyzer, it will only absorb or it will only pass through the Y component ng ating etong light. Ito yung ating original light and meron siyang Y component line and X component line. Pero since the analyzer has a vertical line, only those vertically or the Y component line can pass through. Again, the same the same the same visuals are the same phenomenon is being used in here. Kung ano lang yung finilter mo or kung ano lang yung inanalyze mo, yun lang din yung iyong makukuha. Yun ang kagandahan ni polarizer. So, let me explain this again. The linearly polarized light from the first polarizer can be resolved in components E parallel and E perpendicular. Double line, let me zoom it. Double line stands for parallel and that inverted T stands for perpendicular line. So again, yung ating analyzer will only pass through our parallel or the E parallel. Okay. To our photocell, and the intensity of light from the analyzer is maximal when phi is equals to 0. At other angles, the intensity is equals to maximum intensity cosine squared phi. the transmitted intensity is greatest when phi is equals to 0, and it is 0 when the polarizer and analyzer are crossed so that phi is 90 degrees. As into this, when the polarizer is in here and the analyzer is in here, they can form a degree of 90 degrees, and that will become 0. The intensity is 0. To determine the direction of polarization of light transmitted by the first polarizer, rotate the analyzer until the photocell in figure 3.22. Figure 3.22 measures zero intensity. The polarization axis of the first polarizer is then perpendicular to that of the analyzer. To determine the direction of polarization of the light transmitted by the first polarizer, you need to rotate the analyzer until the photocell measures zero intensity. So, magkakaroon ng zero intensity if they are both perpendicular, or magkakaroon ng 90 degrees, or ito siya is naka-vertical or naka-perpendicular siya kay naka-horizontal, kapag naka-perpendicular line siya kay vertical line ni analyzer, magkakaroon ng zero intensity. And you can determine the direction of polarization kapag nangyari yon. Ano bang use ni polarization natin? In these photos, this show that there's a Polaroid sunglasses whose polarizing axes are left aligned, right perpendicular. The transmitted intensity is greatest when the axes are aligned. It is 0 when the axes are perpendicular. So, when they are aligned, the axes or the transmitted intensity is greatest. Okay? And when they are perpendicular to each other, the intensity is 0. Okay? Left aligned. Ito siya. May nakikita ka pang light or may nagpapass through pa na light. Kapag naging perpendicular sila or vertically aligned, magkakaroon na ng 0 light na nagpapass through. So, in short, wala ka nang makikita. To find the transmitted intensity at intermediate values of the angle phi, the intensity of an electromagnetic wave is proportional to the square of the amplitude of the wave. The ratio of transmitted to incident amplitude is cosine phi. So, the ratio of transmitted to incident intensity is cosine squared phi. Thus, the intensity of the light transmitted through the analyzer is in the equation of Malus' law. Polarized light passing through analyzer. Equation 3.7 is the relationship of a polarized light intensity is equals to maximum intensity times cosine squared phi, where I max is the maximum intensity of light transmitted at phi is equals to 0 and intensity is about the transmitted at angle phi. This relationship discovered experimentally by Etienne Louis Malus in 1809 and is called Malus' law. Malus' law applies only if the incident light passing through the analyzer is already linearly polarized. So, si Malus' law will only apply if meron kang analyzer and polarizer. Kasi si analyzer will only analyze the linearly polarized light. So, analyzer will only analyze the linearly polarized light. Polarization by reflection. Unpolarized light can be polarized either partially or totally by reflection. In Figure 3.24, unpolarized natural light is incident on a reflecting surface between two transparent optical materials. For most angles of incidence, waves for which the electric field vector is perpendicular to the plane of incidence are reflected more strongly than those with which electric field lies in this plane. In this case, the reflected light is partially polarized in the direction perpendicular to the plane of incident. Verse 3.24. So this is a polarization by reflection. You can see in here that this is a reflecting surface. So this is the normal line within this reflecting surface. There's an unpolarized light coming through the reflecting surface, and then it reflects back the partially polarized parallel to the surface. Okay? And these angles are the same. Refracted light partially polarized perpendicular to surface. So there's a reflected light and also there's a refracted light. One particular angle of incidence called polarizing angle, this theta p, the light for which the electric field lies in the plane of incidence is not reflected at all but is completely refracted. Okay? At this same angle of incident of light for which electric field is perpendicular to the plane of incidence is partially reflected to the plane of incident as in this figure. So there's a reflected light and a partially refracted light. In 1812, the British scientist Sir David Brewster discovered that when the angle of incidence is equal to the polarizing angle theta p, the reflected ray and the refracted ray are perpendicular to each other, and in this case, the angle of refraction theta b equals 90 degrees minus theta p. From the law of refraction, Na sine theta p and B sine theta b. So we find the equation of Brewster's law for the polarizing angle. So this is the relationship or the equation for the Brewster's law. Tan theta p is equals to NB over NA. Again, this is from different two materials with their different refractive index NB and NA. This relationship is known as Brewster's law. Although discovered experimentally, it can also be derived from a wave model using Maxwell's equations. Polarizing by reflection is the reason polarizing filters are widely used in sunglasses. When sunlight is reflected from a horizontal surface, the plane of incidence is vertical, and the reflected light contains a preponderance of light that is polarized in the horizontal direction. When the reflection occurs at the smooth asphalt rolled surface or the surface of a lake, it causes unwanted glare. So, vision can be improved by eliminating this glare. The manufacturer makes the polarizing axis of the lens material vertical, so when little of the horizontally polarized light reflected from the road is transmitted to the eyes, the glasses also reduce the overall intensity of the transmitted light to somewhat less than 50% of the intensity of the unpolarized incident light. So, in short, ang kagandahan ni polarized glasses is for lesser intensity of those in unpolarized incident light. Kasi nga 'di ba, kapag wala tayong or sunglasses, we can sometimes be hurt by the intensity of the natural light. Learning activity 3.3, reflection from a swimming pool's surface. Sunlight reflects off the smooth surface of a swimming pool. For what angle of reflection is the reflected light completely polarized? What is the corresponding angle of refraction? And at night, an underwater floodlight is turned on in the pool. Repeat parts A and B for rays from the floodlight that strike the surface from below. For this setup, this problem involves polarization by reflection at an air-water interface in parts A and B. Since it is a sunlight that reflects light in a swimming pool, so the swimming pool will be the water and the air is above the swimming pool. In figure 3.25 shows our sketches. This is the sketch. For both cases, our first target variable is the polarizing angle theta p. This theta p, which we find using Brewster's law, equation 3.8, and for this angle of reflection, the angle of refraction theta b is the complement of theta p, and that is theta b equals the 90 degrees minus the theta p. Okay. Now, for an execution during the day, the light moves in air toward the water. So, Na, which is the air, is 1, and Nb, which is the water, is 1.33. So, from figure 3.8, where's our, from so from this equation, ayan siya. So, NB is equals to 1.33 and NA is 1, or shall we say it is equal to, NB is 1.33 and NA is 1. It is also equal to 1.33. So, tan theta phi is equals to 1.33. To get the theta p, you need to do calculations na arctan. Okay, arctan, value of 1.33. From your calculator, ganyan yan siya, arctan, 1.33. And the theta p is equals to 53.1 degrees. The incident light is at the polarizing angle, so the reflected and refracted rays are perpendicular. And the refracted, or the theta b, in here, the refracted angle theta b is equals to 90 degrees minus the theta p, the reflected angle. So, 90 minus 53.1 is 36.9 degrees. So, this is the okay, 53.31. Theta p, and this is the theta b. So, you can see for what angle of reflection is the refracted and what is the corresponding angle of refraction. So, this is now the answer. This angle in here is also equal to 53.1. Okay? Now, for the next question, at night, the light moves in water toward the air. So now, Na is 1.33 and Nb is 1. Magkabaliktaran na. So, kasi ang sabi is light moves in water toward the air. So, from the water surface, lumabas si light. So, si Na is now the water and Nb is now the air. So, arctan 1 over 1.33 is equals to 36.9 degrees. Now, the theta b is equals to 90 degrees minus 36.9 degrees is equals to 53.1 degrees. So, theta b. Ito yan siya. Transform. Theta b is 53.1 degrees. And see, theta p is 36.9 degrees. Let's continue. Circular and elliptical polarization. Light and other electromagnetic radiation can also have circular or elliptical polarization. To introduce these concepts, let's return once more to mechanical waves on a stretched string. In figure 3.18, suppose that two linearly polarized waves in parts A and B are in phase and have equal amplitude. When they are superposed, each point in the string has simultaneous y and z displacements of equal magnitude. A little thought shows that the resultant wave lies in a plane oriented 45 degrees to the y and z axis. A plane making a 45 angle with the x, y, and z or xz planes, the amplitude of the resultant wave is larger by a factor of square root of 2 than that of either component wave, and the resultant wave is linearly polarized. So what is this one? 3.26. Let's read first. Let's copy first our 3.18 figure and return back to our topic and circular elliptical polarization. Let's move it in here. So, sabi is, tulad ng sinabi kanina, I'm sorry, cannot do this. Okay, let me repeat it. Let's make this like this. Now, since this figure was na-explain ko na kanina, let's recall in this paraphrase na sabi is concept ng mechanical wave, there are superposed in each point. So, just like in this figure, they were superposed, and again, ang lumabas lang is si vertical or the y or the xy plane. Si xy plane. Continue. But now, suppose the two equal amplitude waves differ in phases by quarter cycle. Then the resultant motion of each point correspond to a superposition of two simple harmonic motions at right angles, with a quarter cycle phase difference. The y displacement at a point is greatest at times when the z displacement is 0 and vice versa. The motion of string as a whole then no longer takes place in a single plane. Excuse me. It can be shown that each point on the rope moves in a circle in a plane parallel to YZ plane. Successive points on the rope have successive phase difference, and the overall motion of the string has the appearance of a rotating helix. This is shown to the left of the polarizing filter 3.18c. This particular superposition of two linearly polarized waves is called circular polarization. This is a circular polarization. In figure 3.26 shows the analogous situation for an electromagnetic wave. two sinusoidal waves of equal amplitude polarized in the x and in the y and z directions with a quarter cycle phase difference are superposed. Where's this one? So this is the circular polarization of an electromagnetic wave moving toward you, parallel to the x axis. And the y component of E lags the z component by a quarter cycle, and this phase difference results in right circular polarization. So you as the as my viewer, or we as a viewer, the x component or the x-axis is towards our eyes. So the vision of our eyes is the x-axis, and the y-axis is the vertical, and the z-axis is the horizontal. Again, the x-axis will be our vision of sight, the y-axis will be the vertical line, and the z-axis will be the horizontal line. So circular polarization is the electric field vector of the wave has constant magnitude and rotates in a circle. So para lang siyang ito yung polarized line, and it will be in the maximum kapag na-complete niya yung isang turn. And let's get back to the explanation here. In figure 3.26 shows the analogous. So the wave in figure 3.26 is propagating toward you, and the electric field vector appears to be rotating clockwise. So it appears to be rotating clockwise. So it is called a right circularly polarized electromagnetic wave. If instead the electric field vector of a wave coming toward you appears to be rotating counterclockwise, it is called a left circularly polarized electromagnetic wave. So since this is a right polarized or right circularly polarized electromagnetic wave, let's focus on this figure. If the phase difference between two component waves is something other than a quarter cycle, or if the two component waves have different amplitudes, then each point on the string traces out not a circle but an ellipse. The resulting waves is said to be elliptically polarized. So, ano ang ellipse? Ellipse is just like a circle. A circle is a ganyan. Pero ang ellipse is something like this. Medyo flat sa gitna. Or yung sa gitna, yung may mataba at may payat na portion and may matabang portion. Yan ang itsura ni ellipse. So, the resulting wave is said to be elliptically polarized. For electromagnetic waves with radio frequencies, circular or elliptical polarization can be produced by using two antennas at right angles, fed from the same transmitter but with a phase shifting network that introduces the appropriate phase difference. And for light, the phase shift can be introduced by use of a material that exhibits birefringence. Okay, birefringence, that is, has different indexes of refraction for different directions of polarization. So I hope you have understood what this illustration means. It only tackles about circular polarization, but with an elliptically polarized instead of circular. Let's move on. Photoelasticity. Some optical materials that are not normally birefringent become so when they are subjected to mechanical stress. What is this birefringent, by the way? I'm sorry, naglalag ang ating laptop. Let's be patient. Spelling. Birefringent. Birefringent. Paano siya i-pronounce?
Birefringent.
Okay. So, having two different refractive incidents or indices. So, birefringent is having two refractive indices. So, let's continue. Okay. Some optical materials are not normally birefringent become so when they are subjected to mechanical stress. This is the basis of science of photoelasticity. Stresses in girders, boiler plates, gear teeth, and cathedral pillars can be analyzed by constructing a transparent model of object, usually of a plastic material, subjecting it to stress, and examining it between a polarizer and an analyzer in the cross position. Very complicated stress distributions can be studied by these optical methods. And like in this figure, this plastic model of an artificial hip joint was photographed between two polarizing filters, a polarizer and an analyzer, with perpendicular polarizing axes. The colored interface pattern reveals the direction and magnitude of stresses in the model. Engineers use this result to help design the material artificial hip joint used in medicine. So, ito pala siya ang uses ng ating photo elasticity is sa paggawa ng model or ng mga artificial legs, artificial limbs, ganyan. In figure 3.27, it is a photograph of a photoelastic model under stress. The polarized light enters the model that can be thought of as having a component along each of the two directions of the birefringent plastic. Since these two components travel through the plastic at different speeds, the light that emerges from the other side of the model can have a different overall direction of polarization. Hence, some of this transmitted light will be able to pass through the analyzer even though its polarization axis is at 90 degrees angle to the polarizer's axis, and the stress areas in the plastic will appear as bright spots. The amount of birefringence is different for different wavelengths and hence different colors of light. The color that appears at each location in figure 3.37 is that for which the transmitted light is most nearly polarized along the analyzer's polarization axis. So, in this photoelasticity is just an application of how polarization works in the industry and also in the field of medicine.